Okay, now that we know what transformations are in general, let's talk a little bit about what it means to be a linear transformation. Back in section 5.1, when we were talking about vector spaces for the first time, we said that an n-dimensional vector space was a set of all vectors that had n components where scalar multiplication and vector addition are defined. That means that I can add two vectors together. That's vector addition being defined. I can add two vectors together and get a new vector. I get something else in the same space, in the same vector space. Or I can scale a vector and I get a new vector. It's possible for me to scale a vector. What we're going to talk about now is particular types of transformations called linear transformations. And the linear transformation, the definition of a linear transformation is one in which two properties of vectors hold true within the context of the transformation. And the two properties that we're going to be talking about are vector addition and scalar multiplication. But this time, instead of just adding two vectors together, I'm interested in what happens if I take two vectors and add them together, and then, because that's going to give me a new vector, right? And then perform a transformation on the sum. In other words, what happens if I take vectors u and v and add them together in a vector space? Because it's a vector space, we know that that gives us some new vector called w. But in terms of transformations, what I want to know is what happens when I take the transformation of that vector that I get. Right, that's going to give me the transformation of some new vector w. In particular, what has to happen for this to be considered a linear transformation is that when I add the vectors together and then perform the transformation, I get the same thing as if I had transformed the vectors independently and then added the result together. Let me show you an example. If I have u equals u1, u2, I'm just using u's here because I'm about to create another vector, v, which equals or contains the components v1, v2, then I can talk about the transformation t as being either linear or not linear. But first I need to know what that transformation is. So I'm going to take any arbitrary vector, x1, x2, and I'm going to describe the transformation of t as being what you would get if you added x1 and x2 and for your first component and subtracted x2 from x1 for your second component. To test whether this transformation has the additive property, I need to figure out, first of all, what u plus v is, and that's just going to be u1 plus v1, just using vector addition, and u2 plus v2. And when I transform that, I get the transformation of u1 plus v1, u2 plus v2 is going to be equal to, I forgot my close parentheses there, the first component of this vector, which is u1 plus v1. That's this x1, right? This first component plus the second component plus x2. So to that I need to add u2 plus v2. And then for my second component, I'm going to have u2, sorry, I'm going to have the first component minus the second component. So I'm going to have the first component is u1 plus v1 minus, now I have to be careful here, this is real number addition and subtraction I'm working with here, and multiplication. So I need to use real number properties, including making sure I use order of operations and distribution of negatives and all that kind of stuff. So I have U2 plus V2 in here. And that's going to be equal to U1 plus U2, just changing the order, plus V1 plus V2 for my first component. For my second component, I'm also going to use a different order, but I'll be distributing as I go here. So I'm going to get U1 minus U2 plus V1 minus V2. And then I can make the observation, just using vector addition in reverse, that this is the vector U1 plus U2 and U1 minus U2 plus the vector V1 plus V2, V1 minus V2. And that is the transformation of, the transformation of U, right? That's instead of x1, x2 here, I have x1 plus x2 and x1 minus x2. I have u1 plus u2 and u1 minus u2. So that's the transformation of the vector u. That's equal to the transformation of the vector u1, u2. And then I also have the transformation of the vector v1, v2. So I have plus the transformation of v1, v2. And because adding the vectors together first and then transforming the result is equal to the sum of the individually transformed vectors, because those two things are equal, I can say that this transformation preserves the additive property. Your textbook actually calls that the additivity property. So the transformation T, which does this to vectors, preserves the additivity property because I can either add the two vectors together first and then take the transformation of those, which gives me this, or I can take the transformation of each of the two vectors independently and add the results together, and I'll get the same thing. And I can say that because I've proved it here. For any R2 vectors, U1, U2, and V1, V2, I've shown here that doing one thing, I've shown the transformation here, and then I just reordered some things and came out with the transformation of the sum of the transformations of the individual vectors. So I've essentially proved that for this particular transformation, additivity is preserved. So that's what that means, and we'll do it with a couple more examples in just a minute. But the other property that's critical here is scalar multiplication. And in this context, what we're going to say here, or what we're going to call that, is the homogeneity property. We say that the transformation is homogeneous, or that it preserves the homogeneity property. And I'll talk a little bit more about that on the next screen. Okay, so we say that a transformation preserves the additivity property if you can either add two vectors and then transform them, or transform two vectors and then add them, and you get the same result. We're going to say that a transformation preserves the homogeneity property if you can scale a vector and then transform it, or if you can transform a vector and then scale the result. In other words, if I can do R times V, R is my real number scalar, if I can take the transformation of that, and I can take the transformation of a vector and scale the result, if those two are equal, then we say that the transformation has preserved the homogeneity property. So let's use the same vectors as we did on the previous screen. Actually, we don't need both vectors here. I'm just going to select vector V, which is V1, V2. Because if I did the same things as I'm about to do with both U and V, then the only thing that changes here is this letter, and that's just a generic representation or stand-in, if you will, for some real number. Now my transformation, copied over from the other previous screen, was that the transformation of some vector V was equal to, actually let me rewrite that so we have our dimension as well. Transformation of the vector v1, v2 was v1 plus v2. Ah, I remember now. I did it with x, just to keep it clear. I had x1, x2 here. And that was x1 plus x2 for my first component and x1 minus x2 for my second component. So that's my transformation. In order to test this for homogeneity, I need to figure out what this, remember that scalar multiplication of a vector just produces a different vector, right? So if I'll go down here and I'll say, given that v is v1, v2, r times v is just r times v1, r times v2, right? I can write that way, or I can write it this way. It's actually more common to write those two things in the opposite order. I can say r times v means r times these two components, and there's the multiplication in there. But I can write this either way, is really all I'm saying here. So now what I want to do is test the transformation of this new matrix, r v1, r v2. According to the definition, the transformation's parameters here, I'm going to get the first component, which is rv1, plus the second component, rv2, for my first component in the transformation, in the transformed matrix. And then I'll have rv1 minus rv2. Now, if I went on and did what I had done in the previous screen, I would write this as rv1 plus rv2 negative rv2, but I'm not trying to show additivity here. I'm not trying to show the preservation of additivity. I'm trying to show the preservation of scalar multiplication. I need to try to get this in this form here. So I'm actually going to erase this step because it's not wrong. I've just done some legal vector addition, or unaddition, I guess you could say, but it's not helping me here. So I need to take a different approach. I need to find a way of thinking of this as r times a vector, or r times something, right? So I'm going to, instead of what I have here, I'm going to factor out. Let me make this observation. R times v1 plus r times v2 is a number. This is a single numeric entry here, right? v1 and v2 are just numerical components of a vector, and what I've done is scale each of them. So I can therefore factor out the r. And I'll do the same thing with the second component. Now, using scalar multiplication of vectors in reverse, that gives me r times v1 plus v2, v1 minus v2. But what is v1 plus v2 times v1 minus v2? It's simply the transformation of the vector v1, v2 under, where's my pencil? Close that up. Under this transformation, let me go back up here. Under this transformation, right? This is the transformation of some generic vector x1, x2, x1 plus x2, x1 minus x2. So when I see v1 plus v2, v1 minus v2, I could say that's just the transformation of the vector v1, v2. But the r has been pulled out, and it's only this part that is that transformation. Okay, so that's this transformation here, not the r. The r is not included in the transformation. But what I've just shown you is that I can either, let's see, find rv, r times the vector v, do the transformation on that to get this, or I can find the transformation of vector v, then scale it, right? I can scale the transformation. There's the transformation, scale it, distribute the r, distribute. So I can either go in either direction here. I can start with the transformation, of the scaled vector and show that it equals the scaled transformation. This is the transformation of the scaled vector. This is the scaled transformation of the vector. Very subtle difference there. Or I can go the other way. They're equal. The point is that they're equal. And so we can also say that T preserves homogeneity. I'm going to do one more screen here because I want to show you an example of a transformation that does not preserve. I'm not sure that I'll do both, but one or the other, either additivity or homogeneity. So let's do that on the next screen. Okay, here are my same two vectors, u and v, and I'm going to check this new transformation to see whether it is a linear transformation by checking to see whether it preserves additivity and homogeneity. So the first thing I'm going to do is define what u plus v means. It's the vector u1 plus v1, sorry, the component u1 plus v1, and then u2 plus v2. I'm just using vector addition again. This is what I did on the previous screen. Remember, vector addition just says that u plus v is the components added, the numbers, entries added component-wise. And then I'm going to take the transformation of that. The transformation of the vector u plus v is the transformation of the vector u1 plus v1 and u2 plus v2. And in order to do this transformation, what I need to do is multiply the two components together. And that is, I'm multiplying the components of my u plus v vector because I'm checking to see whether, let me write this here, T of u plus v equals T of u plus T of v. Okay, that's what I'm trying to decide, what I'm trying to check for. And so I've already added the vectors together, and this is what that new vector, that vector addition, the result of that vector addition looks like. This is a single number. This is another single number. It's a two-dimensional vector. And what happens then is I take the first vector, the first component, u1 plus u2, plus v1, and multiply it by the second component, u2 plus v2. And in my second component, I just have the second component of the original, so u2 plus v2. All right, so that is my transformation. Now, I'm going to erase this. It's not as obvious here what I might do to rewrite this vector that I have. I could do, for example, I could actually do this multiplication, right? u1, u2 plus FOIL, right? u1 v2 plus u2 v1 plus u2 v2. Okay, and the bottom is just u2 plus v2. See, what else could I do? I'm looking for a way to write this sum of two vectors as, I'm looking for a way to write the transformation of a sum as the sum of a transformation. And I can kind of see here that this product here, this x1, x2, there's a u1, u2 there, and there's a where is it? Oh, I forgot, I've messed that up here. Hang on a second. Let me fix this. This should be v1, v2. v1, v2, that product. And I can see that there. I see u1, u2, I see v1, v2, I see x1, x2. So that's looking good, but I don't know what to do with these yet. And it's not really terribly obvious. I think what I'm going to do now is take a little break from this approach and try figuring it out from the bottom. In other words, I'm going to say that, let's see, how do I want to do this? Let's just start here. The transformation of U plus the transformation of V, because what I'm trying to do is show that this equals this sum, right? If I can't figure out what to do from this point, then let's start at the other end and see if we can do some stuff here that makes it, the result of that looks like this. The transformation of the transformation of U is going to be U1, U2, and then just U2. And the transformation of V is V1, V2, and then just V2. Using vector addition, I get U1, U2 plus V1, V2, and then just U2 plus V2. That is the result of the sum of the two independent transformations. The U2 plus V2 matches, but the first component does not, right? I have U1, U2 in both approaches. I have V1, V2 by doing it either way, but I have this U1, V2 and U2, V1 in my initial approach, right, doing it this way, that I don't have down here. And there's no way to get them, right? And there's no way to get rid of them here. So that means that the transformation of U plus V and the transformation of U plus the transformation of V are not equal. And that, in turn, means that this transformation is not a linear transformation. It's still a transformation, but it's not linear. I haven't even checked scalar multiplication yet, but I only need one to fail to be able to say this is not a linear transformation. Should I check the other one? I think I'll leave that to you. But I don't need to. I was just trying to see if this was a linear transformation. I could have started with scalar multiplication, and if that had failed, I would also be able to say, without checking additivity, that this was not a linear transformation. Now, here's an interesting thing. We call linear equations linear because each term contains only a linear variable, right? There's nothing squared. There are no squareds or cubes or roots or anything like that. And if you notice that this, I don't know, how do you say this? If I multiply these two components together, x1 and x, these are two real numbers, right? But I'm letting variables represent them. If I multiply these two variables together, then I'm going to have a power of 2. So this kind of a shortcut to noticing that this is not a linear transformation because it's not going to produce a linear result. It's going to produce a squared in this case, not really a squared, but a power of 2. The total power of this component is 2, and so this is destined to fail, right? This is not going to produce the same thing as I have down here. There's an example in your textbook, 6.1.4. It's actually a participation activity that uses, I'll just go down in the corner here. It gives the transformation T of X, they're using X instead of U or V, as being, take the components of X, and they tell you that X is in R2, so it's a two-dimensional vector. Take the components of X and do this with them. Cube X1, subtract the cube of X2, but then take the square, actually it's the cube root, take the cube root of the result. And the second component is just this. Well, I can tell by looking at that that's not linear, because if I take the transformation of the sum, then I'm going to add the vectors together first and then take the cube root. So I'm going to have a single big cube root, right? With a whole bunch of stuff underneath it. But if I take the cube roots, if I do the transformations independently, then I'm going to have two separate cube roots, and I'm going to add those together. So I'll have a cube root of something plus a cube root of something else if I do it one way, but I'll have a cube root of a whole bunch of stuff, a single cube root, if I do it the other way. And you can't just add those together. So this is not a linear transformation. Well, the clue to me is that this can be written as x1 cubed minus x2 cubed to the power of 1/3. Well, that power is not 1, so it's not a linear term. That's kind of a shortcut. When you actually do these for me, when you do them on a quiz, even though you can look at them and say that they're not linear because of the things that I've just described, I still want to see you actually work out all of this stuff. Work out the transformation from one end and from the other, if you have to show they're not linear. Or as we did on the previous screen, do the transformation of the sum and then do the sum of the two transformations to show that they are equal. Turn one into the other. There are actually a couple different ways you can do proofs. You can do them from both sides, and if you meet somewhere in the middle and they are identical, then you've proved it. I prefer to start at one end and work my way down. It's just elegant, I think. The way we did it on the previous screen. You start with t of u plus v, and you work out what that is, and you manipulate it until it looks like t of u plus t of v. And that's my preference. But you can start with t of u plus v and just take it to some midpoint, and then go back and get t of u plus t of v and work it out. And if you can manipulate it so that this step equals this step, if there's some way that you can do that, then that's an equivalent way, just as a valid a way of doing one of these. So you won't see a ton of these, but I am going to ask you to do the steps here. Don't just rely on the shortcuts that I just told you about.